Sam, let's start.
Okay, sounds good. Let me shuffle a couple of pages around here to get everything all organized. Good morning, everyone. My name is Sam Bentley. I'm a marine geologist at Louisiana State University, and I'm doing introductions today on behalf of Paul Liu at North Carolina State to our weekly Source to Sink seminar. Today's presentation is going to be given by George Shua from Louisiana State University. I'll give a little bit more information on his background and credentials in just a few moments. The topic of his presentation is going to be assessing water and mass exchange at the Land-Estuary-Ocean Continuum using a regional Earth system modeling platform. So this lecture series is the brainchild of Paul Liu at North Carolina State and is co-sponsored by the National Science Foundation, Louisiana State University, SCILEC, and the University of Utrecht. So since August of 2020, Paul and the rest of us helping out a little bit have hosted 125 talks. So this to me is one of the great successes from the technological changes that have been foisted upon us by the pandemic, from which I hope we're all recovering now. And all of these are on YouTube, shown here on this slide at the link that you can find, and which it shouldn't be too hard to track down. So it's really a great archive, great for students, great for whatever use you might want to use it for. Next Wednesday, on August 31st, 2022, we're having a presentation given by Mansour Rahman from the Institute of Water and Flood Management at the Bangladesh Institute, University of Engineering and Technology in Dhaka, Bangladesh. The topic of the talk will be implications of incoming sediment and managing the Ganges-Brahmaputra Meghna system in Bangladesh. So really great talk on another world-class system, and we all hope you can make it. Jumping to a little bit more personal introduction on George. George has been working on mostly modeling, but also observations at the land-sea boundary interfaces between rivers, oceans, and the continental margin for the last decade and longer. If you look at his Google Scholar page, you'll see that he's got a number of papers that have well over 100 citations in really diverse areas. I mean, he's looking at large Asian rivers, he's looking at the Mekong, at the Mississippi, and developing new modeling platforms. So quite frankly, George is doing better right now than I was at his stage of career. So kudos to George for that. He's been at LSU since 2014, I believe. He's an associate professor now in the LSU Department of Oceanography and Coastal Sciences, where he also has a joint appointment with our High Performance Computing Center, the Center for Computation and Technology, and he's finally a fellow in the LSU Coastal Studies Institute. So very excited about the talk, and George, I think we can turn it over to you to get started. Thank you very much.
Thank you, Sam. Let me share my screen. Can you see my screen?
Yes.
Okay. Can you hear me, right? Yeah. Okay. Yes. First of all, thank you, Sam, for the good work as always. And I'm glad to be here. Today, I'm gonna present mostly the research over the past 8 years. As Sam just introduced, I've been Louisiana State since 2014, and I'm starting the 9th year at LSU. So the topic I will cover is assess water and mass exchange at Land-Estuary-Ocean Continuum using a regional Earth system modeling platform. So instead of focus one topic, I think the purpose of my presentation today is to kind of like overview about what my groups, mainly my graduate students, achieved over the last 8 years. So let's start it with this like traditional source to sink figures. So source to sink, like when I was a PhD student at NC State, we focused mostly on sediment transport, how sediment is yield and how they are delivered into like land surface and river channels, and then being dumped into the ocean, and how all the oceanic process gonna resuspend this sediment, and then finally how they will be distributed. That is how we call it a source to sink. But in my eyes, in addition to that layer, I have a little bit different, not different, it's like more broad understanding about source to sink. So I think instead of like we focus merely on sediment and the geological processes, the coastal and land interaction zone, or we can call it a land-estuary-ocean continuum, is probably the most complicated system on the Earth. So in this system, we can see that we have definitely, I would say, like atmospheric forcing will control everything. Everything starts with the movement of wind, precipitation, and then we have a process. We have the interaction between. We should have interaction for all this process. I want to address that. I believe there should be. We should always care about the interaction. For example, we started from atmosphere. We need to care about the interaction between atmosphere and the land surface. And once the sediment is or associated nutrients are generated, how they will be delivered into the coastal ocean, and what is, in that regard, what is like coupling between these two systems, and back into the ocean, how the ocean will affect the dynamics of the atmospheric circulation. So this has been my long-term career goal, is try to build up this system. And the question I would like to answer via this presentation is, first, how about the sediment and nutrient dynamics in response to this kind of like short-term violent eventual disturbance, such as tropical storms, cold front? The second is that in addition to sediment, how about like nutrient and carbon? We know that like land, no doubt, serves as the major source in terms of sediment, nutrient and carbon. So in addition to sediment, what's the impact of nutrient and carbon in the coastal ocean, and how they're going to be cycled in the ocean? And the last one is that how about the exchange right here? How about the exchange at the land-ocean interaction zone? So bearing all these questions, I have been trying to look into a system that can connect all these like different processes. It's turned out that right in our backyard at SU, not far away, for example, I just measured that the direct distance between my backyard and the Mississippi River is less than 4 kilometers. So why not we choose this system? And so we have a Mississippi River discharge a huge amount of fresh water, sediment, nutrient, and carbon into the Gulf of Mexico. And I know that this seminar series has a lot of like international like audience. So to help you to better understand the system, I list some like facts compare with Mississippi against Yangtze River in China and the Mekong River in South China Sea in Vietnam. So you can see that all three rivers are large rivers, and different is that like the delta of Mississippi River is located in a subtropical environment. Yangtze River is in a temperate environment. Mekong is in a tropical environment. And they all discharge to kind of like a marginal ocean, right? We all know, I think this audience, I don't have to explain what is a marginal sea, but in terms of Mississippi, the destination of most of the Mississippi River is gonna be the Gulf of Mexico. The size of the Gulf of Mexico is slightly bigger than that of East China Sea, but it's about half of the South China Sea. So just give you some background about like what this system looks like. And this system has been like disturbed by all kinds of different processes. There is like an individual and a long-term threat. For example, most notorious, like in the Gulf, we have recurring hypoxia happens almost each year in the Louisiana, Texas shelf. And we have like more and more like major hurricanes. For example, last year, Ida make landfall in Louisiana, and the track of Ida is about 50 miles away from my house. And of course, land loss. The Louisiana suffers a lot from land loss. This map shows that if we don't do anything, if there's no human intervention, what is the coastline gonna looks like in the 50 years from now? And in addition to hypoxia, hurricanes, and land loss, we also have like harmful algae bloom mostly in Florida waters, but more and more we began to see some harmful algae bloom showing up in the northern Gulf of Mexico as well. So we need to understand this kind of like a huge system that has been troubled by different kind of like coastal disasters, right? And my talk today and my research at the LSU over the past 8 years has been mainly develop and apply this we call the coast modeling system. So if you are not a modeler, so COAST stand for the coupled ocean, atmosphere, wave, and sediment transport modeling system. It was originally developed by John Warner and colleagues at NC State back in 2010. And at that time, so it's mainly the weather model, weather research and forecast WRF model coupled with the original ocean model, ROMS, and then have a wave model, can be either SWAN or WaveWatch3. And one of the contribution from my group over the past years is we successfully introduced a land, surface, and hydrology model into this COAST platform. So most of my talk today, I will talk about the application of two-way. When I talk about a two-way or three-way couple, for example, in the next, I will first start with some hurricane-introduced sediment transport. That kind of study is a three-way couple, which means that we coupled a WRF model with ocean model with SWAN model. That's a three-way couple. And also, I will give some examples about how we couple ROMS with SWAN to study some relatively longer-term sediment dynamics, for example, fluid mud. And then I will give some like update on in the ROMS region, like how this coupled we call physical biogeochemical models application in the Gulf of Mexico. And in the last section, I will focus on our recent development in WRF hydro, including successfully introduced the first ever sediment module into the WRF hydro model, and also a state-of-the-art coupling method between ROMS and WRF hydro. So as I said that like one of the purpose of today's talk is I also want to summarize what my students has achieved over the past years. So as I mentioned that our team at LSU, we not only apply the model to like Gulf of Mexico or to like Mississippi River, we also do tons of like model development. So here I'm just list some of the modules or models developed at LSU. So for example, we have a wave supported fluid mud module that is embedded into the CSTMS, the Community Sediment Transport Modeling System. And also we have a sediment-induced light attenuation algorithm, which couple the sediment dynamics with the NPZD model on the platform of ROMS. And as I just mentioned, we introduced a process-based sediment model into the platform of WRF hydro. And we also have two in-house NPZD model. One model is we have this like fully coupled nitrogen phosphate silicate cycle with oxygen dynamics. And we also have an in-house carbon model, which accounts carbon from not only river, but also including the carbon introduced by land loss. And in the last but not least, we recently developed a dynamic coupled ocean and river model that is the coupling between the ocean and the river region. So my talk in the next, I will organize them into mainly 4 topics. So the first is I will start with some sediment dynamics. And the second is nutrient and hypoxia. And we know that hypoxia has been mainly introduced by riverine nutrient. So I consider that as a source to sink as well. And the third, chapter 3, gonna be a land loss and how that can contribute to the ocean acidification in the Gulf of Mexico. And the last, I will give some example, a case study. We shift the gear a little bit to North Carolina, where we apply the first ever land-ocean coupling to understand the sediment and water dynamics during a hurricane event. We focused on compound flooding. So first, this is whenever I try to summarize my research, this is always my first slide because this is a wonderful work done by my first PhD student, John, who is now a postdoc scholar at Hui. So back in 2018, we successfully coupled a WRF model with ocean model and wave model. And within ocean model realms, we have this very mature sediment transport module. So what I'm showing here is a hand cast of Hurricane Gustav. So you can see all the figures I'm showing here is animations. So by the way, I will not show many model validations for the sake of time, but if you are interested into that, you are more than welcome look into the papers for very detailed, robust model calibration and validation. So what I try to demonstrate here is that using this three-way coupled model, we can successfully represent not only the atmospheric oceanic process, but also the sediment dynamics. So for example, if you take a look at this panel here, you can see what I'm showing here. This is the suspended sediment concentration whenever the hurricane made a landfall. So all the animations are synchronized. For example, here we are. See, this is approaching of Gustav. And also we can quantify the net erosion and net deposition after a storm event. So we all know that hurricane not only introduce erosion. On the left-hand side of the track line, there could be a deposition. So right-hand side erosion, you can see here the red color stands for net erosion, but this eroded sediment, sometimes they can be dumped into the left-hand side and form a kind of like depot center. So following on that, John further developed the model, and what he tried to understand is that how about we connect sediment dynamics with primary productivity in the coastal ocean, and how this turbidity introduced by a hurricane event can further affect the primary productivity in the coastal ocean. So for this application, we first run a 20-year coupled. Here, I mean, the coupled is physical coupled with NPZD with the biogeochemical model. And then we extract the conditions, which including physics and biogeochemical conditions at the exactly date when Hurricane Gustav is approaching. And we put that into a three-way coupled model. So in addition to that, like we successfully introduced a sediment attenuation, the light attenuation introduced by sediment, this term, into the model. So we can easily have two experiments and compare that. The benchmark run where we consider no influence from sediment in terms of light attenuation. And the second run will be a sensitivity test with sediment introduced light attenuation. So again, for the same hurricane, if we take a look at this transect here, I'm not sure if you can see my marker here, and from bottom to top, we are looking at sediment concentration. And the chlorophyll, if there is no sediment introduced light attenuation, with the chlorophyll is simulated once we turn on the light attenuation introduced by sediment. So again, in this case, we are coupling atmospheric model with ocean model with wave model, and within the ocean model, we turn on both sediment and NPZD model, and at the same time, we introduce the light attenuation from the sediment. So the application of this kind of simulation is that, for example, if without sediment-induced light attenuation, you can see 1 week after the landfall of Gustav, this is what the coastal ocean looks like in terms of chlorophyll A surface. And if we turn on the sediment-introduced light attenuation, this is what the chlorophyll A gonna be look like. So our conclusion is that with light attenuation introduced by sediment, a lot of nutrients which are supposed to be consumed in the shallow water will be instead being exported to the open ocean, which introduce this we call the post-hurricane algae bloom. Next is we focus in this region. Here, again, this is a Mississippi River Delta, and this is the satellite image showing the Atchafalaya River. I think Atchafalaya River is somewhere here, and then this is the sediment plume. But for this application, what we try to look into is not like sediment dynamics, is sediment dynamics, but it's not like suspended load. We try to focus on the wave-supported fluid mud, which has already been reported by Sahin and Travasky et al. They have this like tripod mounted with ADCP and backscatter and found this laminar flow of high density fluid mud. So what John has done is he introduced this wave boundary layer. It's kind of like a sandwich between the water column and the sediments and the seabed in the community sediment transport modeling system. So I will, for the sake of time, I will not go to all the details, and but quickly just show how this like wave boundary layer looks like. We focus on a handcast back in 2008, March 2008, when we have 3 cold front passing this area. And maybe in next slide, you will see it's more clear is that here we compare 2 simulations. This is two cross transact, I think somewhere here. And if we take a look at this transact, if there is no fluid mud module, and this is with fluid mud. So we can see that we have 3, this is wind speed, and we have 3 cold front passing this area back in March 2008. And whenever there is a strong wave activity, you can see this is the lotocline that has been simulated by the new fluid mud model. Yeah. I see Courtney here, and many thanks Courtney for providing us this like detailed comments when John is composing this paper. Thank you, Courtney. Okay, let's move to chapter 2. In this section, I will focus on some development in a couple of the physical biology or chemical model. And the 2 examples, one is the river nutrient and hypoxia. So this is a photo from NOVA, and it shows that this distribution of hypoxia stands for whenever the water, if you are not a ecologist, hypoxia stands for whenever the oxygen level in the seawater is smaller than 2 milligrams per liter. So over the past, almost 40 years, NOVA has been continuously monitoring the distribution of hypoxia. And they also try to set they call the HTF, Hypoxia Task Force goal. And they try to reduce the hypoxia area by half. And what they want to do is to reduce the nitrogen load from the Mississippi River. And we know that in general, the development of hypoxia is more or less correlated with the amount of nutrient delivered by the Mississippi River. So in this application, we built this is Yanda's work, and we built a in-house like NPZD model, mostly based on the NAMRU model by Kishi et al. So what different is with other application is that we have more sophisticated plankton biomass structure. So we have 2 groups of phytoplankton, and we have 3 groups of zooplankton. And also, in addition to nitrogen and phosphate cycle, we also have a silicate cycle. And we all know that diatom is probably the most important plankton in the northern Gulf of Mexico. And the right-hand side is just a snapshot of the hypoxia water development back in 2019, which was the largest hypoxia year recorded. And you can see whenever you see a reddish color means the water is hypoxic. So the first justification of like put all this kind of energy into a hypoxia model is that, so for example, to the right-hand side, this is a panel-to-panel comparison between model simulated hypoxia water distribution and this shelf-wide cruise happens every year. You see all these measurements backlit here. This is the cruise happens every year. It's mainly in early summer. So you can see the panel-to-panel comparison. Our model can capture in general, the magnitude, the spatial extension of hypoxia pretty well. But if we look at the time series, there's more interesting dynamics about the development of hypoxia. So let's see, for example, 2020. So what do you see here? This is the time, and this is the area of hypoxic water. So the cruise back in 2020 happens on the day 211. So which means that at that time, the hypoxic water area is very limited. And if you cruise that time, you will find, okay, this year, the hypoxia is not that bad, right? Which matched pretty well with our model. These bars are model simulated hypoxia area, and this horizontal bar, this stand for the area reported by the annual survey. But if we look back, we can see that the model tells us a different story. Instead of a relatively small year, 2020 is actually there's a very serious hypoxic issue as well. And the reason we all know that is that the Hurricane Laura break down the summer stratification on the Louisiana shelf, and that is why if you have a cruise after the hurricane, you can almost always expect a minimum hypoxic water distribution. Another application, talk about the task force action plan. So the task force action plan is that we reduce the nitrogen load by 50% by a certain amount, and possibly we will have a minimum hypoxic water, right? So, but our model shows a different story. So, for example, in this application, Yanda conduct a series of different numerical experiments with nitrogen input, phosphate input, silicate input compared to current condition. So we read, for example, this N20 stand for what if we reduce the nitrogen load by 20%. And this experiment here stand for what if we reduce the phosphate input by 80%, right? And all the way to the bottom, what if we reduce all three nutrients by 80%? So you can see that this reduction to the right-hand side, this shows the hypoxia area among these different experiments. The horizontal bar here, I'm not sure if you can see here, is not standing for time. This is standing for different experiment. So you can see, for example, this is a control run. We are right here, okay? And this is the current hypoxia area. And to the left, you can see that this is when the experiment found a hypoxia area increase. And to the right-hand side, we can find this is a hypoxia area reduced. So if we take a look at this experiment, if we reduce nitrogen, phosphate, and silicate all by 80%, then we can see a significant drop in hypoxic water. That's for sure. But interesting here is that if we move to the left, certain experiments show that in this kind of experiment, for example, let's see P40. So if we only drop phosphate by 40%, instead of a reduced hypoxia area, the hypoxia water, the size of the hypoxic water body is going to actually increase, right? So which implies that these very complex food webs in the coastal ocean, if we only use one nutrient, one phytoplankton, one zooplankton, sometimes can barely solve the problem. A very similar analogy I want to use here, just think about the rabbit in the forest, right? So you can see, for example, in the forest, if we think about this is phytoplankton, right? We must have different kind of zooplankton to consume this phytoplankton. And if we only have grass, rabbit, and fox, the story is gonna be much different. So indeed, what we found here is that this kind of like task force action plan might need to put more consideration about the different combinations of nutrient reduction. Next chapter, chapter 3. Here, I want to focus on carbon dynamics. And this is a Wijun's paper back in 2011. Many of you already see these figures many times. What Wijun proposed here is that for a marginal ocean system, we have a carbon dioxide exchange with the surface ocean. And if the carbon dioxide elevated in the air, the surface ocean gonna become more and more acidic. And from source to sink view, we also have a huge amount of river input, right? So for example, in the Gulf of Mexico, we see a lot of DIC, dissolved in organic carbon discharge from the Mississippi River. And in general, this kind of carbon budget can be well balanced. But whenever I moved to LSU, I realized a serious problem is that how about land loss? So this is, I already showed this figure one time. So the land loss in Louisiana, you might know that the rate is 1 football pitch per hour. So on the left-hand side, just to show you that how serious this land loss could be. So this is a photo I took by my student Le, and she has been mainly focused on carbon modeling. And during her field trip back in 2020, about 4 weeks after the 2020 cold snap, we can see the shoreline already retreat for about 1.5 meters. So this happens in this small bay we call a Barretera Bay. So then the research question here is that what is a sink, or what is the fate or destiny of the carbon that will be released from the eroded soil, and how that might contribute to the ocean acidification, or how that will impact the water quality in the Bay Area and the coastal ocean. So in this application, what we do is we use this coupled physical biogeochemical model instead of focus on nutrient and oxygen. Here we focus on carbon cycle. So we first performed a 20 years model handcast of the entire Gulf of Mexico, and which produced very good carbon conditions. For example, on the left-hand side, just to quickly show that we use all kind of model calibration. This is a comparison of model simulated sea surface carbon dioxide. Here, this is from January to June, compare with satellite product. So you can see that our model can well resolve the carbon dynamics. And over the past 20 years, what we found is that if we talk about the Gulf, because if we try to understand the Barretera Bay, first of all, we need to understand what the Gulf is going on, right? So we can see this uptick of sea surface carbon dioxide, and also dropping of pH value. So no doubt the Gulf of Mexico is getting more and more acidic as well. So then back to the small bay, the Barretera Bay. Again, right-hand side, I'm showing some model data comparison at a buoy located here. So we have temperature, salinity, and sea surface carbon dioxide. So you can see that the model can well capture, in blue color, can capture the dynamics recorded on this buoy. So what our development in this component is that we successfully introduced this land erosion into this carbon cycle. So in other words, is that our model not only consider the carbon from a river, from the atmosphere, from the ocean, open ocean, but also we take in the carbon released from the eroded soil as a boundary condition. So in this case, you can see the animation here overlaid with land loss map, this Barretera Bay. Specifically during summertime, you can see this reddish color stand for oversaturated sea surface water. And this is mainly because of the carbon released from the eroded soil. So back to the source to sink theme, that the land contributed to the ocean, not only sediment, but we also need to understand the contribution from nutrient, from carbon, and all pollutants, all these kind of materials. So move forward, and in the next, which is also going to be the last chapter of my presentation today, is that I will talk about some new developments in this regard. So this is where we coupled process-based hydrological model with RAMS model, and on top of that, we introduced the sediment model into the hydrology model. Some background about warp hydro, since this is still a relatively new model. I think warp hydro gained its popularity back in mainly in 2015 during the Colorado flood, and so this model is process-based model. Has been mainly development by Steve Garcia's team at NCAR. So essentially, there are three components. So there is a land surface model, and which will provide the land surface condition back to a atmospheric model. At the same time, it will receive the precipitation. And once we have precipitation, first of all, the water will be pumped into warp hydro model and go to subsurface. And once subsurface is oversaturated, the surplus water will be returned back as a surface sheet flow. And if there is more water, this water will be drainage into the channel. So there's three different routing. We have subsurface routing, we have surface routing, and we also have a channel routing. So this warp hydro model until now is still the operational model for the national water model by NOAA National Water Center in Tuscaloosa, Alabama. It provides this river channel discharge over 2.7 million river reaches. This is not a GIS-based model. This is a process-based spatially distributed hydrological model. So the development here is that this is my student Daoyang's work. So he successfully coupled the hydrology model with ocean model. So the company strategy is that we let the ocean model and the hydrology model share a similar computational grid. Right? So, but we have a fixed boundary. So instead of like, I know that if you are familiar with most of the storm surge model, EarthCirc, FVCOM, they have this like usually they have a, including the traditional RAMs, they usually have a wet and dry. So like they mostly have ocean model handling the inundation on the land side. But different from that is that what we do is that we force a hard boundary at roughly the 0 meter isobase, and we let the two models talk, exchange like water levels, velocity, and sediment along this boundary. So this is just a scheme about how this company was realized. So we first have like warp hydro running and then provide data to the boundary. Then we'll have RAMs running, provide data in the boundary. And as a boundary, we use a model coupling toolkit to compute the, for example, water level. Then we convert water level to velocity and use this velocity as the updated boundary condition back to the hydrology model, back to the RAMS model. And so all this cycle will going on. So the application here, I will shift my gear a little bit, is that we focus on Hurricane Florence, which made a landfall in North Carolina. Dongxiao has two papers. One is already published. The other, I think, will be published soon. It talk about like the rainfall pattern and also the simulation of use warp hydro to simulate the hydrological dynamics in this watershed. This is a Cape Fear watershed in North Carolina. And Daoyang's work here is to focus on the ocean land coupling. So we have a parent model. This is John Warner's Southeast, US Southeast model. And within that, there is a first child model is Carolina model. And you can see this tiny little square here. This is the model domain I just mentioned, where the ocean model and the hydrological model share the exactly computational domain, and their boundary is somewhere here. Okay, and the horizontal, for information, horizontal resolution is about 100 meters. And this is just a zoom in about estuary. This is the Cape Fear estuary. So for this setup, to demonstrate like why we need this kind of like dynamic coupling, we performed, of course, a standalone like control run, which is here. So this is a control run. We call it experiment 3, where we turn on the coupling. And we can also have a standalone runs, which is going to be the experiment 1, where we only run runs, but with the ocean model, but we turn on the wet and dry. And compare with a one-way coupled. Until now, I believe most of the so-called coupling model between land and ocean are still one-way coupled, or we can call them linked model, where we extract national water models export at these 2 points and use that as boundary condition to drive the ocean model. And of course, we can have other sensitivity tests in addition to the control run. We can, like, for example, we can turn off the precipitation by the hydrology model, so we can isolate the impact from ocean only. And we can also turn off the wind in the ocean model. In that case, we will only look into the impact from the land flooding or river flooding. So this is an animation, just to give you a general idea about what it looks like. And if we use a linked ROMs, so this is, again, this is where we extract the solution of national water model and apply the river discharge provided by the national water model as a boundary condition to drive a ROMs with wet and dry turn on. So this is going to be the condition looks like. And this is a coupled model solution here. We use the default physics schemes by Wolf Hydro, which is a simplified 719 style. They call it diffusive wave. This is, we talk about the condition. Diffusive wave means the physics schemes by the Wolf Hydro. And here to the right hand side, this is more advanced. So this is a new development by Dao Yang. He introduced the inertial term into the Wolf Hydro. So you can see that right hand side, these two models, this shows the result of our fully coupled model compared with this, like if we only use ROMs forced by the output from the national water model. So this is what it looks like as an estuary. So you can see if we focus on the estuary, again, this is when we couple. We use a national water model to drive the ocean model. This is a coupled model, but use Wolf Hydro's default physics. And this is use a new physics of Wolf Hydro. Both these two cases are fully coupled model. What I want you to see here is if we make a transect along the estuary here, and we stretch it, you can see how the water level will develop as the hurricane is approaching. So for example, right now the hurricane is here. As the hurricane made a landfall, we began to see the water level shows different among the 3 different experiments. Specifically about 1 week after the landfall, we can see the tail of the black line, which is the linked ROMs, began to showing a much elevated water level. And compared to that, our coupled model shows the maximum water level at this end is about 1.0 meter. Right? You can see in the background, I put an airboat. I always use this analogy. So in this case, we try to build an airboat that can cruise not only in shallow water, but also in wetland and land. So how good is this coupling method? So you can see here, this is a water level comparison at 2 of the NOAA buoys. One is here, face open ocean, and the other is here at the top of the estuary, right here. So you can see as open ocean, all these like 4 different experiments shows in general a good agreement with observation, right? But in the estuary, the story can be different. If we only use ROMS model if there's no river input, so this gray line here shows the result. But if we use the input from the national water model, we use like when we coupling to drive the model, we can show this overshoot of water level. But use our coupled model, doesn't matter, use updated like new method or the default method, they all showed a much better agreement, specifically after the landfall of Hurricane Florence. So another application of this model is that we can also identify the nonlinear effect and also how much compound effect we can find in this system. So I will not go to the details, but in general here, the nonlinear effect stands for whenever the compound is river and ocean working together and how much they are bigger than if we only have river flood, if we only have ocean surge, right? So you can see that this compound effect is mainly in this area, right? And to the right-hand side, we can also see what is the influence if we participate the influence from river compared with the influence from the ocean. And whenever you see a number one, this means like river is 100% dominant. Whenever you see a bluish color, which means ocean is 100% dominant. So you can see river is mainly controls the maximum water levels here, but ocean will control estuary and also this junction zone. Okay, I have one second. Another application is that we can also build this kind of like water budget, because like in this case, we have a model coupling along this entire coastline, right? So we have water get into the ocean model, we have water flow out of the ocean model. And in this case, we can consider this estuary as a closed box. And we can divide this hurricane introduce the compound flood into different stages by different like the performance of wind and surge. But the major conclusion here is that what we calculated there is that the Cape Fear estuary has been washed more than 10 times within 20 days after Hurricane Florence. And this lateral land input to ocean here can be very important. Again, if we use this like one-way couple or linked model, we can only get input at these 2 points, but use our new method, we can account the input, or not only input, but also output, because this is two-way coupled or dynamic coupled along all these coastline. Then the next step is that back to the source to sink, right? We focused on the coupling between land and ocean in terms of water. How about sediment? So in this is Dongxiao's work, and he introduced the sediment module into Wharf Hydro, and this like sediment model is nested both on the channel routing and surface flow routing. So these two processes here, and you can see that all this model is under the umbrella of Wharf, and this side, this is Wharf Hydro side, and this is the traditional coast side. But now with this new application, we can also exchange water level and sediment between land and ocean. And for the sediment model, just like ocean model, we have different groups. We can group the sediment by sand, silt, clay. They can have a suspended mode, deposit mode, and eroded mode. And all we do is a bookkeeping. So with this kind of like technique, we can finally get, I would say this is a real source to sink, right? So this is, we can see this to the left-hand side, this is water storm surge, sediment concentration, and this is net erosion deposition. And in other words is that now we can close the cycle. We have this process that can represent all the way from wind, from precipitation, and how they will affect the water, and how affect for water will impact the sediment yield, and how the sediment yield will later on, how the sediment yielded will be delivered in the channels and all the way to the ocean, and then experience all this deposition and resuspension. So this is a dynamics showing that, and you can see this is a net erosion and deposition computed by this coupling model system. For example, the brown color means a lot of deposition. This means like this sediment will be washed from the watershed and dumped into the river channels. And in the ocean side, most of the sediments will be accumulated either in the river channel, or they can be transported all the way toward the east. So the next step is that I just want to give you a quick update is that, as I said, that like the system I always interested is the Mississippi and Gulf of Mexico. So this is some new model result. So in this case, we are developing this 250-meter Mississippi River model. So this just shows some preliminary results of a handcast for the condition back in a flood event back in May of 2010. On the left-hand side, what you see here, this is stream flow. And to the right-hand side, this is sediment, suspended sediment concentration. So you can see that even from this animation, we can observe this kind of like rainfall pattern, right? So as there is rainfall is moving through this system, the rainfall will generate the sediment, and the sediment will be dumped into the river channels. So this is going to be a summary of my talk today. I know there's a lot of information here. So, but all these are centered on this, I call a regional Earth modeling system. So we need this kind of toolbox to solve all kinds of processes on different scales. For example, we need to understand hurricanes, then we need to focus at least like the Gulf scale. We need to understand atmosphere. And if we try to understand like how soil erosion can contribute to ocean acidification, then we might start from a like small base scale. And in terms of hypoxia, nutrient source to sink from river, how that will affect the water quality, we'll look into the shelf scale, right? And all these developments, this is centered on this like coupled modeling system. So this is my last slide. Acknowledgement. First of all my collaborators, specifically John Warner from USGS, and also my colleagues at LSU, including Sam, Kevin, and also we have a new project with WIMS. We now collaborate with Courtney on this as well. And I also want to give a big sum up for all my grad students, former and current members. They are these like the scientists who are really doing the heavy liftings, all this, and of course funding agencies from like federal level, state level, and last but not least, the support from LSU, the Office of Research and Economic Development, led by Sam, and also LSU High Performance Computing. A roughly estimate is that the work I'm showing here has used at least 100 million core per hours of computation. That's a lot of money as well. Last, I'm looking for PhD student and postdocs. So if you are interested in this kind of research, you want to work with us, please contact me without hesitation. That will be all, Sam. Thank you.
Great job, George. So we have time for a few questions, and also I'm going to have to jump off early because I've got to go meet with my boss in a few minutes. But yeah, George is the biggest user. His team is the biggest user of computational units in the state. So go, George. Any questions from anyone?
I can ask a question.
Yeah, sure, Marty. Yeah.
First, thank you for a great talk, and you know, a lot of impressive work that you showed. It's interesting to hear that you're the biggest computational user in the entire state. That's quite a lot. But I guess the question well, there are a lot of questions I could ask, but I'm really interested in your results where you showed the study for the effects of different nutrient reductions, and how even when some nutrients were reduced, you would have an increase in hypoxia. I thought that was really interesting. Is there any pattern to that, or was it just kind of seemed kind of random which combinations led to that?
I wouldn't say random, but for example, you can see here is that to the right-hand side, this panel shows in addition to hypoxia area, and Yanda also plot like the concentration of like small phytoplankton, large phytoplankton, zooplankton. You can see that we can see in general, there is some correlation between the large zooplankton and predictory zooplankton in terms of the hypoxia area distribution.
Mhm.
So we can also show some spatial pattern, but just like the more we dig into this, the more we feel it's like this, like I see this is like the rabbit problem. It's not that like easily isolate like which is the source, which is the dominant one, but we do need to a very comprehensive evaluation about who and work with who will control this entire dynamics. Yeah.
Mhm. Are there any broad conclusions of what is needed to do to actually have a reduction?
Yes,
like-
for sure. You can, for example, you can see here, if we look to the right-hand side, here, this curve, and if we want to achieve a 50% reduction here, one of the experiment we can expect is we purely reduce silicate by 80%. If we keep nitrogen, but only reduce silicate by 80%, we can also achieve this goal according to our model. Yeah, we could be wrong for sure.
And that's a silicate coming from the rivers or from the
That's a silicate from the river. Yeah, you're right. Yeah.
Because that's interesting because so much effort is placed on nitrogen.
Mhm.
Yeah.
Hello, George. I am from Bangladesh. My name
Hi.
is Mansur Rahman. Yeah,
Yeah, you will be the next
quite-
speaker.
it's quite interesting work you did for a long time. Especially for the system level work, the information and data is a very difficult task to gather together because you are working in a large basin, coast, and the riverine area.
Mhm.
So I'm curious to know how the real life information data you could capture that we are also experiencing similar problem in Bangladesh because Bangladesh is sharing basin with other country.
Mhm.
And I think it is different from our country that you are experiencing. If you have any comment or suggestion, then maybe helpful for us.
I think one of the benefits working on the Mississippi Gulf of Mexico is the open access of almost all the data. And I do understand your concern because I used to work on the Mekong, which was shared by like 6 different countries. But for Mekong, I know that there is organization called the Mekong River Commission, which is kind of like a coalition of the lower 5 countries share the Mekong River Delta. Share the Mekong River Basin. I'm not sure for the Ganges and Bangladesh if you have this kind of similar mechanisms that data can be shared freely within at least the scientific community. But also another thing is that a satellite, I would see like satellite is mostly you can get satellite data freely from NASA's website. I think if you're doing like a sediment related research, at least a satellite can give you some idea about like surface turbidity.
Thank you. Thank you.
I think Samuel has already logged off. Okay, any other questions?
I could ask another question that's more kind of systematic, like I'm just so George and I and other people on this call, we all work within a community model, the coast community model. And how do we share? I'm curious how George's approach to sharing the code is. Like the code I've developed that my group worked to develop, we did try to put it into the coast branch, and that did happen. But you know, I'm just curious how.
Yeah, that's a good question. Yeah, I think this is always up to the, how to say, this is the main developer's priority, right? So for example, like for the coupling model, I know that in the most recent coast release, this like one-way couple, at least Wolf Hydro is already including in that coast platform. And but there are also other platforms. Like I think the best way is we can make some like standalone module. I think that's the best way to share this code. So for example, recently the sediment module, at least the serial mode, like the Wolf Hydro sediment model, Dongxi already published that on an open source platform, HydroShare. So we can. This is another alternative. And then the other thing is that we can share the model code like via some like model training workshops. For example, there is coast modeling training workshops. And I would say like, I do understand like there's a lot of pressure in terms of the main developer in terms of incorporating all this code into their system. They have their own priority, and most of them like they works by themselves or have a very limited support, like in terms of like code updating. And they also have their interests. For example, like if they want to focus on data simulation, they will always give like priority for that kind of code. This is a question. I think I also have this similar discussion with Saeed at Nova. And the bigger picture here is try to build something like module. And so we can plug into any platform, but I know we have a long way to go in that regard.
And when you say any platform, you mean any Coast ROMs implementation?
Coast ROMs like FVCOM, even for these like unstructured or unstructured structures. But if we can have some like sharing, not platform, something like that, it will be good. Yeah.
Hey, George, there's a question in the chat room.
Yeah.
Are you able to see it?
Oh, okay, let me see. Sure. Draw research a specific model like SWAT. Yes, Wolf Hydro is a standalone hydrology model. It's different from SWAT and HSPF because SWAT and HSPF, based on my understanding, is mostly GIS based. This is kind of like use a lot of regression, and you have all these sub-basins, right? So, but the Wolf Hydro is a process-based, spatially distributed. So we have, just like ocean model, we have all these different, we have all these Akiva C grid. So you can define, so actually all the process is computed by grid instead of like sub-basin by sub-basin, if that answers the question. And how you simulate the nutrients from industry or wastewater medicine? That's a good question. If the industry or wastewater is willing to provide us this kind of like information, we are more than happy to introduce that into as a point source into our model. Yeah. This is durable, but it's based on if they would like to release that kind of data. Yeah.
Okay, good. George and Courtney, ask both of your question because about the sediment, I mean the nutrient and even pollutants from the bottom sediment, the resuspension. So what's the status of the evaluation of that? For example, particularly after a storm, the resuspension could stir up and contribute. Is there any? We know we talked about a decade ago, you know, is there any good assessment now?
Well, I'll say from my group, the PhD work of Julia Moriarty works to put in tracers into the sediment model that can be, that could represent contaminants in the sediment bed. She used it to represent organic carbon and particulate organic matter, not contaminants. But a project that George and Kevin and I have ongoing now is to kind of take that module and use it to represent mercury contamination. So that's kind of ongoing research is to take the code that's developed and then instead of using it for nutrient type matter, to use it for contaminants. And from a modeling point of view, it's just a matter of changing rates and changing the geochemical equations in the sediment component of the model to represent the contaminant instead of a nutrient.
Yeah. I mean, the good thing for working on Gulf of Mexico, because every year there's some storm coming, and then you can test, you can validate the simulation. So the big challenge is because many estuary or modern river dominant marginal sea is those inventory in the sediment, and how long will it take for the system to clean itself if we completely shut down the import. And there's still a big question, but I think maybe you guys, maybe after a couple of years, maybe can answer a question. Okay, anybody else? Any question, any comments? Great, if not, this talk is also archived on the YouTube channel. So if anybody, any research group, your student want to go back to rewatch this presentation, you're welcome to go to our Source to Think YouTube channel to rewatch them. Okay, otherwise, thank you, George, and thank you for everybody for giving this wonderful talk. And I hope I see you next week about Ganges Brahmaputra talk. Okay, thank you.
Bob. Yeah, thank you all.
Okay, yeah, bye-bye. Martha, you will stay here for a couple of minutes?